All right, well, good afternoon, everyone. Today we're going to be talking about mechanical shock, and we're going to really be looking at what is mechanical shock, what kind of failures it produces, and some of the simulation strategies for mitigating or designing product that are robust for mechanical shock types of environments. So when we're talking about mechanical shock, it really can cause three different things. We have cyclic fatigue. So this would be, low-level mechanical shocks that occur multiple times that can either cause elastic events, which would be high cycle fatigue, or low cycle fatigue events, which really there's a very fine line between low cycle fatigue when we're talking about mechanical bending or overstress, because anytime I inelastically deform the solder or the metals on a circuit board, there's a good chance that I'm going to have an overstress failure as a result. So just a little bit more into that, mechanical failures, we're talking overstress, which is a low cycle, high amplitude from shock or bending, or we're talking high cycle, low amplitude vibration, repetitive shocks. So low amplitude events, we want to see elastic type of deformations, and then we're talking about getting into high cycle fatigue, so like 100,000 or more events. Okay. As I said, anytime we hit the yield stress of the solder joints, even the yield stress of the copper leads or any other metals on the circuit board, there's a good chance we're going to break something. The weird thing about, well, I don't know if it's a weird thing, but one of the things about electronics is that a lot of the fracture strengths of the materials are all very similar. So ceramic capacitors crack are usually between 30 and 60 megapascals, maybe 80 megapascals. Pad cratering is around the same type of stress level. And then the yield stress of the solder is actually, 30 to 50 megapascals. So you can imagine, as soon as I start yielding a solder joint, there's a good chance I'm going to break something. So low cycle fatigue of the metals usually is going to be the Kaufman-Manson equation. And really we're looking at events that occur 100 to 10,000 cycles. Once you get below 100, it's really, is it an overstress, or, it really gets very difficult to predict very low cycles of failure if it's a bending type of event. So we're using the Kaufman-Manson equation, which is, an elastic strain range. And then for high cycle fatigue, we're using a Baskin equation, which could be elastic strain or stress, because those are directly proportional when we're elastic. So we're also looking at things that occur hundreds of thousands of cycles, such as maybe car door slamming, doors, anything that's sort of lower level types of amplitudes. Why is it advantageous to do simulations? It's really to catch problems before they're identified in validation and production. So we're trying to identify design issues at the conceptual and design phase, where we can add additional mount points, we can make the board thicker, we can add stiffeners, we can change component selections, and it really is easy for us to do that earlier, and it's actually a lot cheaper. So as the product goes through the development cycle, the cost of making design changes or fixing issues becomes very expensive. The levels of testing for mechanical shock, where there's component level testings. These are usually on the loose packages, and typically it would be for the old school hermetic type ceramic packages, where a lot of sort of low volume hand soldering type of operations where the part may be dropped, and we're talking about the individual electronic component, and maybe something could get shaken loose inside the part. So really not for most standard overmolded package. Component level drop tests are usually not applicable. There has been some indication that dropping tantalum capacitors could have some issues even in overmolded state. So then we have assembled package level testing. This is really component package qualification type of testing. This is coupon level testing, where I solder a new package onto a test coupon. I subject it to a very high shock level, typically 1500 Gs, half milliseconds, really for cell phone types of environments. And then we get to subassembly and assembly level types of drop testing. When we're talking about overstress, it really is, I mean, yes, you can break the component package, but really it's going to be the interconnect structure. This could be, pretty much what's on either side of the solder joint itself. They're very difficult to predict an overstress failure because it really is a, high strain rate type of event, crack propagation through a very brittle material for the most part. And typically we see it as a random failure distribution. So, if we're at overstress type of levels, the probability of failure on the first drop would be the same as the 100th drop, so a random sort of failure distribution. And that you'll see in, when you look at Weibull data for shot drops to failure, the beta is usually 1, which indicates sort of random. When we're talking sort of classic mechanical shock simulations, this is usually what comes to mind would be cell phone drop simulation. So, as far as, the key thing is to determine what is the actual loads being applied to the circuit board inside here. But this is sort of where, and it really was with the mobile phone market, really when free fall drop test simulations came into, sort of in vogue, where people started doing a lot of them. But the key thing is, what is it actually doing to the circuit board inside there? But we have to remember that mechanical shock events can occur at multiple points during the assembly process or post-assembly. So it could be, after soldering. It could be in ICT, in circuit test, where you have a bunch of pogo pins that are pneumatically actuated that push down on the board very rapidly, providing a lot of force onto the board. It could be heatsink attachment. It could be connector insertion, depaneling. We see a lot of, sort of bending, or, really we're not talking, it's not a drop, but it is a very rapid application of mechanical stress, and that can cause failures of the electronics. Another thing that is very similar to mechanical shock is just excessive flexure. So, everybody's sort of, there's a big deal about bending of cell phones and things like that. So, and what we're seeing is, there's been a lot of 4-point bend testing for, and it is to test to make sure the packages are robust with regards to mechanical shock, because it's a very high strain rate 4-point bend test. And then we also see the more adoption of what we call a 9-point bend test. We have 8 spherical supports and then a center point. Again, all mostly for mobile phones or mobile electronics. But classic mechanical shock was due to shipping and transportation. It's things going on to trucks, being dropped by the UPS guy, kicked around, but we're also seeing mechanical shock due to, in portable medical devices, or really anything that's sort of roller-mounted test equipment. What we saw were fairly decent shock levels developed when they went over threshold. So floor transitions, cable covers, going into an elevator that's not quite aligned. You could get a 1-inch drop fairly easily going over a cable cover, and that could result in failures or heat sinks shaking loose. Environmental definitions, usually it's height or G level and what type of surface, orientation of the drop, and the number of drops that needs to survive. So just an example of some of the specs for test service condition test levels from JESD 22B110. Really, it's equivalent drop height, what's the peak acceleration, and what's the pulse duration. And these are all things, peak acceleration and pulse duration are easily translated into a load, something I can, actually figure out. But telling me, I'm going to drop this from 44 inches, what's the equivalent G level? It really depends on what the housing is, what it's attached, how the board's attached, what's it hitting, So really, when you come down to mechanical shock specs, I like to see acceleration and time because I know how to simulate those. Typically, you know, what we're looking at for, and a good example is BGAs, really would be probably the most common component that shows shock-related failure. And most of these parts, it really isn't the mass of the component itself. Yes, it can be if there's a big heat sink on it. But usually it's board bending. It's really, you know, we don't really care about the mass of the part. If I shock the component in plane, and so if we, you know, the package wants to move with respect to the PCB sort of in a shear direction, there's a lot of solder attached. So really in the shear direction, we don't really see any issues. It really is more of a bending event when you get like a peeling stress at the corners, which exerts a large tensile load on the solder joint, which can cause it to fracture at the brittle interfaces. When we're looking at the brittle interfaces, really we're not talking about failures in the solder ball itself. We're talking about fractures at the intermetallics, which are on both the package and the PCB side, and we're talking about pad cratering, so pulling out of the, actually breaking the epoxy where the copper is attached to the board. Those are overstress types of conditions, and you wouldn't expect to see those at 100,000 types of events. You're going to see these very low cycle, large acceleration type of events, and you're going to cause a brittle fracture where a crack can propagate very quickly through these brittle materials and cause a failure. What do they look like? So we have an intermetallic fracture here on the top. You can see the crack. And now intermetallics are normal. They're how the solder bonds to the printed circuit board, or to the copper. In this case, looks like we have a nickel layer up here, and we have a copper intermetallic down here. So this would be a tin nickel intermetallic on the top, a tin copper intermetallic on the bottom. And the intermetallics themselves are fairly stiff, high modulus with respect to the solder, and very brittle. So under an overstress condition, they're not going to plastically deform. You're going to get a brittle crack, and it's just going to propagate very quickly through that interface. Same thing down here. Really stress is a function of cross-sectional area. So when I have a very small copper pad, there's going to be and I'm pulling this part, I'm going to have a very large tensile stress in my circuit board, and I can actually pull the circuit board apart underneath the copper. Ceramic capacitor cracking here is just an example of a board bending event due to shock that cracked a ceramic cap. Just definitions of pad cratering. It's crack initiation within the laminate during a mechanical event, such as ICT, and we talked about board depanelization, connector insertion, shock and drop. So that's pretty much the definition of a pad crater. The thing about pad cratering is, it's one of these failures that you may not see during electrical test. What will happen is if the trace doesn't crack here, this is still electrically functional. So what you're doing is letting escapes into the field where there's not much holding that solder joint onto the board except for a very small portion of copper, which could break under a little bit of more mechanical load. Just some more pictures of it. We also saw a little bit of an uptick in pad cratering when we went to lead-free because of the stiffer solder, and a lot of the laminates, we had to go with higher glass transition temperature laminates. They tended to be a little bit more brittle than the typical laminates we were using before. And it really is very difficult to detect. As I said, it's very hard to see it with an X-ray. Really, to pick it up, you're going to have to do dye and pry or some destructive technique in order to determine whether or not you have pad cratering occurring. Usually what happens is you have an electrical failure after some assembly process or some drop event, and you go into destructive analysis right away. Some of the solutions, it may be using a different type of laminate, so doing some type of testing on the laminates themselves, doing design changes on the pads, making the copper pads larger, and using solder mask defined. That would, there's kind of a trade-off there. If you make the copper pad, you're spreading the stress out or the force out over a larger area and reducing the stress. But by going to solder mask defined, you're actually increasing the stress on the intermetallic. So there's kind of be a trade-off. The thing is they break around the same stress values. So when you do a drop test or shock test, you'll see mixed mode. You'll see intermetallic fractures. You'll see bond pad cratering sort of all mixed together. But really what we're looking at for sort of mitigation of pad cratering is limiting the amount of strain on your board during assembly. During ICT, you may have to add mount points. You may consider going to a different solder, but my opinion is that if I have a shock problem with SAC 305, yes, switching to a SAC 105 or an SNC or SN100 or a SAC M may get me a little bit of margin, but I still have a problem, and I'm still going to have failures. There's just not enough. Yeah, there's a little bit, but there's just not enough to eliminate the issue. It may be a combination of solder changes with additional mounting to mitigate it. Intermetallic fractures, it's a fracture through the intermetallic. They're typically an overstress. We wouldn't really see this during low cycle or high cycle fatigue. What we see with high cycle and low cycle fatigue are cracks in the bulk of the solder. So if you start to see cracks like this in the intermetallic on a unit and you try to convince yourself that this is vibration or low cycle fatigue, chances are it's not. It's somebody dropped the unit or did something to it. And the intermetallics are there, all the time. They're irreversible. They're a function of how the solder is held together to the copper. It occurs rapidly during reflow, but it still grows as the solder joint ages. And just some guidelines on how thick it should be. As it gets thicker and thicker, if you look at this type of chart or these actual pictures of the intermetallic growth of tin copper intermetallics, if you can imagine if I had a crack and it wants to crack through this intermetallic here on the lower left-hand corner, as the crack propagates through the intermetallic, it's going to hit ductile solder regions and it's going to be arrested, and it's going to have to sort of work its way through the plastic material before it hits the brittle material. So that kind of slows it down, makes it a little bit more robust. But as I grow that layer thicker and thicker, now I've got this very uniform intermetallic structure where the crack can just zip right through it and break. So that's one reason, at least one of my theories. In fact, one of my colleagues at the University of Maryland came up with that theory. Now why, there's a large difference in strength when you have a very thick intermetallic versus an intermetallic that's very spiky or sort of like a mountain range. The crack cannot propagate without hitting a ductile material. Another issue that can reduce strength during shock, Kirkendall voiding or microvoiding. Kirkendall voiding is due to excessive intermetallic growth. This type of microvoiding is more of an effect of organic contaminants in the copper plating solution. And so they pretty much figured out how to get rid of that. Not something we have seen recently, but what happened was people, during the lead-free transition, people were looking for reasons why lead-free boards were failing, and they did cross-sectioning and saw these microvoids, but then they did cross-sectioning on tin lead product and saw the same microvoids, so it wasn't really a function of lead-free. But again, any type of voids or things at the interface or in the intermetallics, again, you're reducing the cross-sectional area of the attach, you're increasing the stress, which can cause earlier failures during the shock event. As I was saying earlier, there's tin copper intermetallics, there's tin nickel intermetallics, electroless nickel immersion gold ENIG is that's the gold finish on your boards. It's just a very thin layer of gold over top of nickel. The standard intermetallic, well, that's going to be the standard intermetallic form would be tin nickel. For any of the other board finishes, such as OSP, immersion tin, immersion silver, hassle, you're going to be forming copper tin intermetallics. And as we can see on this chart here on the right, the number of drops to failure for the copper tin intermetallics is quite significantly higher. So, if you're going into a high shock level environment, you may be better off going with the OSP or hassle type of finish because you're getting a stronger intermetallic. The other thing, though, is ENIG is really good for elevated temperature applications because at higher temperatures, the tin nickel intermetallic grows quite a bit slower than the tin copper intermetallic, so it's usually better for high temperature applications. So there's things you have to consider about all the different board finishes and how they impact the shock robustness of the product. Definitely a thing of concern is with lead-free, it is a stiffer solder. It does put more stress on the interconnects. Therefore, it does have a weaker, its number of drops to failure is typically lower. So this is just a good example of that. You have the yellow line, which is tin lead. And then you have your standard SAC 305 here on the left. So definitely a significant reduction in the drops to failure because of intermetallic fracture and pad cratering. Because the yield stress of SAC is much higher, the solder doesn't deform and absorb the stress. How to mitigate for pad cratering or intermetallic fracture during shock. Really, we talked, and we'll go into some simulation later on with the effect of mount points and board thickness. Here we're looking at, things I can do that are sort of outside the design, really sort of, corner staking, edge bonding, underfill, and how do they affect shock robustness. These are sort of, hey, I've got an existing board. I can't do anything about mounting. I can't really change the form factor of the circuit board. Is there something, I've got a part that's failing, is there something I can do to prevent that? Just some different loading conditions. Sort of what's the minimal, this is just another example of just adding a little bit of staking on the corner just to sort of glue that part down, and will that have an effect? And yes, just a little bit of staking. This just shows you how sensitive shock can be to just a small mechanical change to the system. So the staked joints lasted quite a bit longer. At least time to first failure was about 2x higher. Once you start getting out here, it doesn't really matter. We're starting to get into low cycle fatigue type of action here above 100 cycles. But definitely time to first failure. So, and really that's, is somebody going to drop it more than 10 times? Hopefully not. But adding a little bit of shock, a little bit of staking will get you a little bit of margin. When we go to sort of more, and these are those 3 coupons I showed, so a little bit more, a larger volume of staking. We have our tin lead, which is the green line. We have some lead-free, SAC 305, SN100, and then we have 2 different corner stakes, a UA 2605 and a 1583. So yes, there's a function of the corner staking material. But you can see all these now are very close. Looks like there was one early failure here on the red, but definitely purple. There's only 3 failures. In fact, you can see there's quite a bit of number of suspensions here. So definitely the corner staking that had a significant impact on drops to failure here, where we were getting drops within 20 cycles. Now we're starting to get drops 70 to 100 before we see the first failure. Adding a little bit more of epoxy, call it doing an edge bond, which you're doing a sort of an L around the corner. Again, now you're seeing more of an effect. Is that the 1583? Okay, the 1583 is actually performing better than the tin lead. This material probably needs to be a little bit harder. It's probably still a little bit too soft, but it's still being better. But now when we get to underfill, we have 0 failures for the underfill device. So you can see just a huge impact using underfill. Now, underfill is great for vibration and mechanical shock, but you have to make sure when you're selecting an underfill, especially, typically what we're seeing is if I'm putting my product into an environment that has high shock levels and high vibration levels, it probably also has high temperature changes or thermal cycling criteria. So you just have to make sure that whatever underfill you pick, and some extent goes to edge bonding and the corner stakes also, you want to make sure that that underfill or staking compound is compatible with the temperature ranges that you're using and doesn't actually cause a problem when it comes to thermal cycling. When we get to simulation and prediction of mechanical shock failures, we're going to start sort of, the old school technique using Steinberg methodology for predicting number of shocks and drops to failure. Really, it was more of a go, no-go type criteria, which, and based on displacements, which when you think about it, really makes sense, and because as soon as I get into a low cycle fatigue type of behavior with a shock event, there's a good chance that I'm going to break something due to overstress, because the yield stress of solder is close to the breaking stress for a lot of these materials. So I like the no-go, no-go approach. But this is an older technique and really is based on displacement, and we know that surface mount components are really more sensitive to strain or bending of the circuit board. So this is an example. This is IPC 9704, which had a strain. How fast was the strain being applied, and then the board thickness, and what's the permissible strain that I could subject that component to for mostly for BGAs. So if we look at the prediction for Steinberg for shock, now it's not a straightforward. It is a fairly complex calculation, because you have to predict. You compute out the Z. I should put some subscripts on here. There's a Z critical. That is the critical displacement, which I don't want to exceed in order to have if I exceed it, I'm going to have a failure. And it was just an empirical equation that I'm showing here, 00132 times the board length, a component factor, the thickness of the board, position constant, and again, we're assuming that the board shape during the shock event follows usually that's a sine cosine type of function, and then the square root of the component length. And then the printed circuit board displacement during the shock event is this equation. It's a function of the natural frequency, because the board natural frequency is sort of an indicator of how stiff that board is. The G level and 9.8. However, how much G level is actually effective on that printed circuit board is dependent on the natural frequency of not only the board, but also what is the frequency of the shock pulse itself. So there's a table in Steinberg's book, and I would definitely recommend anybody interested in shock and vibration should have a copy of Steinberg's book. But what I have to do is I actually have to modify the G level based on the pulse duration and the natural frequency of the board using what we call a frequency ratio. And there's a table, it's a graphical chart or table that you have to look it up on in order to modify that G level. So here are the modified. So for that example, we have 3 G levels with 2 different time pulses, their effective frequency, and then what the effective adjusted G load is. So you can see actually the most damaging level here is the 1000 G 1 millisecond, even though we have a 1500 Gs here. It's just that this frequency of the pulse is fairly far away from the circuit board, so it's just not doing as much as the 1000 G pulse. And then if I put it into the equations, it pretty much says my Z limits for that part depend on a BJ. Usually you're using a component factor of 2.25 or it's around 2 something. It's been modified a couple times for BJ devices, which means I can have about a 73 mil deflection. If I had a leaded part, usually your component factor is 1, it would be at least 165 mils. But you can see here the actual Z deformation during that shock pulse, or the calculated using the Steinberg equation, is much higher than both of these. So this would be a no-go type of prediction. Again, that would be just for the center component. The components that are farther away from the edge are going to have a lower displacement. Chances are they may be shown as passing. But really what we need to do for BGA devices and low profile, QFN devices, is we need to know what the board level strain or how much bending that device is being subjected to. So when we're talking FEA simulations, we're talking a transient dynamic simulation. We typically, for speed and doing things rapidly, we use what we call implicit transient dynamic. The example I showed earlier of the cell phone drop, that's an example of an explicit transient dynamic simulation. So explicit is used when things are hitting each other, or impacting. What we're talking about for an implicit is, hey, the shock level comes in through the mounting points of the board, gets transferred. Now I'm not hitting anything. There's no impact, like a capacitor moving and hitting a wall or a car crash or something like that. But I can still do a curvature-based assessment using Steinberg. Again, this is using a simplified approach, saying, oh, the board is bending in a circular shape. I can convert deflection. And again, there's also equations for sinusoidal shape. What I do is, based on the deflection and the board span, I predict out what the curvature is, and the strain at the component is just a function of curvature and the board thickness. And so using that type of criteria, we can see that the board level strains are above 1,000. For a leaded component, I would have a 1,400 microstrain type of limit. For a BGA, it would be about 622 microstrain. And this, if you think about it, if you're familiar with sort of some of the guidelines coming out for BGA devices during depaneling and ICT, we're usually sitting around a 650, 600 to 750 microstrain type of limit for those parts during a shock event. So these are right in the ballpark saying, oh yeah, we still have a problem. The Sherlock software is what we use as sort of a custom pre and post processor for doing mechanical shock simulations. It utilizes an FEA code in the background, either Calculix, ANSYS, or Abacus, and we're currently working on Nastran support. But it's a way to rapidly build up electronic models, FEA models for electronic assemblies, and it just greatly reduces the amount of time required to make these fairly complex circuit board models. We do that with a combination of built-in libraries, either part level, package level materials. You can see, overmold BGA, tin lead solder, part parameters, built-in boundary conditions such as standoffs, a way to input the shock profile very rapidly. Again, now, being a circuit board type of software, we're assuming that the shock levels are coming in through the mounting points. So if you think about it, if in a free fall drops situation, the board's screwed to something like a chassis, that chassis hits the ground, it transmits the acceleration through the mounting points. Now the board wants to keep moving, the mount points stop, so it is that type of simulation. We're not hitting the board with a hammer or something, or dropping on a ball onto the board or something like that. It does come in through the boundary conditions for the board. We also have the built-in stack-up tool, and there are different levels of detail that you can put into the stack-up or how you want to model your circuit board. There's, sort of homogeneous approximation based on the copper content and the layer thickness, so you come up with effective board properties. But, if you have the computational power, you can get all the way down to layer level modeling. Again, there's some difficulty associated with doing layer level modeling when copper layers are only 18 to 40 micron thick. You're talking, some fairly thin, high aspect ratio finite elements, which can cause an issue. But it's just something to be aware of. This, I think, is an interesting example. This is the FEA results for a shock pulse that's up 1500 Gs, half millisecond. The one interesting thing is, yes, as we showed before, you have to adjust the G levels based on the natural frequency of the board, and the effective G level actually becomes quite a bit lower based on the natural frequency. And this is just a pretty good example of that, where because that shock pulse is fairly short, the actual maximum displacement of the board doesn't occur until after the shock pulse is done. So, it's a half millisecond pulse. The maximum deflection of the circuit board doesn't occur until at 1 millisecond. So pretty much the shock pulse is done, and then the board is actually starting to catch up to it. The other thing to show is that the FEA is showing about a about 0.2 inches of deflection, and if I know the natural frequency, I can actually get a very good deflection value out of the Steinberg prediction of about almost the same number. That's that's sort of expected because, as I said, the natural frequency is a good indicator of the stiffness or the structural rigidity of that circuit board. There's no reason to believe that a spring mass system wouldn't give you the right deflection based if I have the right stiffness values for the spring. But again, here's the difference between a displacement criteria and a strain-based criteria. So, and this is another thing that you can think about when you're laying out a circuit board is, am I forming what we call sort of alleys or actually hinges on my circuit board? You can see I've got a large concentration of strain or bending because of the way this board has been laid out. And actually these 9 components in the center have very similar strain levels, so they're all going to have very similar time to failure, drops to failure, because they're being subjected to about the same types of board level strains. And then, where Steinberg wouldn't predict parts, at lower doses of failing, a strain-based criteria would. The other thing that would also predict is if I had a component next to a standoff where I get a lot of bending, that part would also be flagged as being at risk of a shock failure. So that's one thing where a displacement criteria is just going to miss, and you really should be using a bending criteria. Just I wanted to show some examples of some shock simulations. This is just a simple model of a ceramic quad flat pack. Again, these parts are notorious for having sort of in-plane type of motions. This is the Sherlock simulation showing that part. This is a shock pulse in the X direction of the board, so an in-plane shock pulse that's causing this part to displace to the right. And you can see these leads are bending sideways. We use a combination. Again, this is, finite element simulations of electronics are pretty complex, and one of the reasons for that is we have this scaling issue. We've got fairly large circuit boards and then very fine copper features or leads. So you're talking about a circuit board that could be, 8 to 12 inches in length, and then you're talking about leads that could be 150 microns thick. And I don't know that in mils off the top of my head. So, that makes it difficult to model, but we use a combination of tied contact surfaces, so I can tie dissimilar meshes together. And you can see here as I'm getting the lead strains for the strains in the leads, the strains in the part, the strains in the leads, and then we actually get, because this part is moving back and forth, we actually have low cycle fatigue prediction for those leads as a function of time. In this particular case, I think it was 100 drops spaced over 10 years. So this is saying, bound, probably going to get about 10% failure after about 70 drops. Another example of sort of a mitigation strategy with, and this would be another common part that we see failing with an electrolytic capacitor. Two-leaded device. Sometimes if they have a little bit of excessive standoff, or they're not supported enough, they're relatively large mass, fairly thin leads, you will get differential component motion during the shock event. So this part's swaying back and forth. With the software action add, I can go from about a 0.9 millimeter deflection during the shock event. By just adding a little bit of staking to one side, I can actually cut that down to, a tenth. So where it would fail without staking, it will pass with the staking. So that's just an example of, how it can show the effect of staking. When somebody asks, well, do I need to, it's an added assembly, step. People, want to know if it's necessary to prevent a failure. And with this, you can actually show them, yes, I can put staking and prevent the failure. Additional mounting point considerations. What's the difference having 4 corner mount points versus, some other mounting configuration? This is just a simple example. 4 corners. And I like this because it also shows that that hinge effect, because I've got a clear span on my board. The board is much stiffer where these parts are. The board's going to want to bend at the most flexible point. And if I leave spans like this open, it's going to concentrate all the bending to a localized region, and then parts that are on either side of that bend may be at risk of failure. So you're seeing that here with these center parts being at risk of failure, and parts near standoffs. So here's the parts near standoffs that are at risk of failure also. All these parts that are highlighted in red are at risk of failure. But if I add a mount point in the middle, my deflection goes down, to about 1 mil versus, that's still not, we had about a 0.1 deflection, and we knock it down by almost 2 to 3 orders of magnitude, so I'm no longer getting a lot of deflection. And this board now passes. A more sort of exaggerated impact of that, this is a very large CPU card with a DC to DC converter mounted to it right there. You can see its natural frequency is very low, 35 hertz, so it's going to bend a lot. Right now we're getting about 12 millimeters of deflection. Again, you see that effect of having sort of clear spans. You see wherever there's components, the bending is reduced. It's really when I come off that stiff area and go into the circuit board, I'm going to get concentrated bending. You see a lot of failures. But if I add 2 additional mount points, again, this board is about 16 inches long. For this vibration environment, it's still not sufficient to have 6 mounting points. Putting just 2 additional ones in the midspan, I would probably have to do even more. But I did cut down my deflection from 12 millimeters down to 1.65 millimeters. I worked on this. I just wanted to show the effect. Again, a common question I get is, what happens if I increase my board thickness? As you increase your board thickness, you are adding additional mass to the circuit board. So again, force is equal mass times acceleration. If I have a thicker board that has higher mass, I'm going to have higher force applied to the board. But on the flip side of that, the stiffness of the circuit board is directly proportional to the moment of inertia, and the moment of inertia of that circuit board is a cubic with respect to the thickness. So your stiffness is going to increase quite dramatically as I go increasing the thickness. And the thing is, will my stiffness sort of outweigh or the additional mass that I've added to my circuit board? And the answer is yes. If we're looking at a 1.5 or a 1.6 millimeter thick circuit board, I'm almost getting 1 millimeter displacement. As I get to thicker and thicker boards, my deflection is reduced quite a bit. The one thing I probably should have shown is, what's that mean in function as a function of strain? I did not put that on here. I'll have to add that for next time I give this talk. Because again, as you get to a thicker circuit board, for a given displacement, the strain goes up. So I had to double check. Definitely we can control the displacement. Got to double check on the strain. But in conclusion, definitely simulation is necessary to capture complex boundary conditions. We're going to have complex mode shapes. The highest deflection may not be at the center of the circuit board. We have to account for the strain at the boundary conditions. When we're looking at sort of these displacement-based techniques, you're making a lot of assumptions. And then high displacement is not always indicative of high stress. And you do still need to know what the natural frequency, to get the good results, you still need to know what the natural frequency of that board is. And then, the simulations can definitely identify high areas of curvature, as we showed. Can you avoid sort of forming these alleys where you're concentrating curvature, looking at the effect of board thickness, looking at the effect of component motion, and then the effect of mitigation, staking, adding boundary conditions, things like that you can do with the simulation.